Tangent and normal vectors. We will try to explore as much as we can about what happens with acceleration in terms of the particle that moves. Um, we want to be able to eventually uh, use uh, the acceleration to solve for um, the so-called area um, of a smooth curve, and then also the energy that's being exerted from this particle as it moves out in space. That becomes our long-term goal. With it, we're going to build the mechanics. We're going to build the mechanics that determines all that information. So we can use this so-called tangent vector. Um, we can use this normal vector to try to uh, uh, build the so-called cylinder by which fluid would flow through. If it is fluid that we're trying to measure the volume of it, um, uh, we have the measurement tools would come by the so-called unit tangent vector and then also the normal vector. We use these guys to help us do that in chapters uh, 15 ultimately, chapter 14 where we just only talk about volume and how to calculate it. But then in chapter 15, how we can use the tangent and particularly the normal vector to be able to produce the measurement for fluid flow itself. So we start with two fundamental principles in analysis, and that is the tangent vector and then secondly the normal vector. The tangent vector is defined on, if you think about it, this so-called the velocity of the particle divided by its magnitude. That gives us, they call it here a unit tangent vector. Why is it a unit? Because when you divide any vector by its magnitude, it becomes a unit vector. What's a unit vector? If I take capital T and take its norm, I get 1. That defines this idea of a unit vector. The normal vector is defined off of the tangent. That is, if I take here the derivative of this tangent, then I get the so-called normal. The normal vector wants to try to, in some kind of way, measure acceleration. So from the normal vector, uh, if I'm trying to get acceleration, if I take the second derivative on r double prime, obviously that you have in the numerator, and that gives us some formula for here, this normal vector. Let's see. So here we call that the principal unit normal vector, and it's just the tangent vector, its derivative divided by its magnitude. Now graphically, let's see how they look. If we take a curve, some curve given by this position vector r of t, and from a particular point, we have, as the curve is moving, as the curve moves in space, if I stop at a particular value, we can calculate its so-called tangent. The vector that is perpendicular to the tangent is said to be its normal, normal or perpendicular. The normal vector always points to where the acceleration is moving toward. See, this guy is curving back this way. We want to be able to give the name of the vector, or really the number, that wants to calculate the acceleration with respect to the normal, and then to give a number to the acceleration with respect to the tangent. Wow. That's what we want. And if the math was easy, we could get it real easy. Sometimes the math here becomes more algebraic, and so it takes us a little while. So what are we after? We are after the so-called components of the acceleration. The acceleration vector, according to this theory, very classic theory in mathematics, the acceleration is said to lie within the plane of the tangent and the normal vectors. Well, it says if r of t is the position vector for a smooth curve, the word smooth here means that it's continuous, especially at its endpoints, and the endpoints, all of its derivatives exist. We haven't talked about partial derivatives, right? Okay, that's later on in this class. I get mixed up. Sometimes my head is like in differential equation mode or linear algebra mode, in which we assume even partial derivatives. So anyway, we'll define that a little bit better later on, but a smooth curve means that it's continuous, especially at the endpoints, and that all of its derivatives exist. And later on we'll talk about with x, y, and z, you have partial derivatives, and they exist as well. So if r of t is a position vector for a smooth curve, and that the normal vector does exist, then the acceleration vector is somewhere in the plane of the tangent and the normal vectors. A sub t and a sub n are said to be components or numbers, right? Scalars. Said to be a coefficient, the coefficient of the tangent, some number there, we call it a sub t. And then there's some coefficient for the normal, a sub n. It's just the coefficient. We say it's there. Now those numbers are helpful. If I look at this particular curve here, if I come from this point, and then we have the tangent vector, and then I look at its perpendicular, see how this particle is moving in this direction? So where the curvature is, right, where it concaves, that's the direction for the normal vector. So this normal vector goes this way. When you measure, if you want to give a measurement for this tangent vector, some distance with respect to the acceleration, and if you want to measure this normal vector with respect to acceleration, we have the components for t. A dot with t is the component, the tangent component for acceleration, or the tangential component for acceleration. And then if I want to measure here the normal with respect to the acceleration, we have its component, a dot n, or the centripetal force, if you will. And here, this a dot n is called the normal component for acceleration. So look, this is not red. This is a sub t, and this is a sub n. So if you go back up, The acceleration is said to lie within the planes of the tangent and normal vectors produced by this linear combination here with the components a sub t and a sub n. A sub t is this tangential component of acceleration, and a sub n is this normal component of acceleration. How do we find them? This tangential component of acceleration, it's just the dot product of the acceleration and the tangent vector. How do we find a sub n? This normal component for acceleration, it's just the dot product of the acceleration and the normal vector. Now, that's all that I use. Now, all this other stuff that they have in there, I don't keep that in my head. I just keep what's easy, and I use that, and I'm done. Right? Because I can remember that a sub n is a dot n, and a sub t is a dot t. Now, here comes the work part. Find the unit tangent vector to the curve at the specified value for the parameter t. So we find first r prime of t, that's 2ti plus 2j. And then we must find its norm, r prime of t, is equal to the square root of 2t squared plus 2 squared. So this norm here is 2 times the square root of t squared plus 1. Inside 4t squared plus 4, I just factored out a 4, took the square root of that. So the tangent vector t of t is equal to 2t over 2 times the square root of t squared plus 1i plus 2 over 2 times the square root of t squared plus 1j. Now we evaluate the tangent vector at 1. You know, the 2's cancel out there. So this is just 1 over the square root of 2i plus 1 over the square root of 2j. Oh yeah, here's something to note, that the normal vector and the tangent vector are perpendicular. That means that their dot products are equal to 0. This is all you needed there. What about this one? Let's do the same thing. R prime of t is equal to negative 5 sine ti plus 5 cosine tj. We find its norm. That's the square root of the negative 5 sine t to be squared plus 5 cosine t all to be squared. So it gives us 25 times parentheses sine squared t plus cosine squared t. Just gives us 5, right? Yeah, sine squared plus cosine squared is 1, so you have left under the radical 25. So the square root of 25 is just 5. So the normal vector, r prime of t divided by its norm. So this is the negative 5 sine t divided by 5i plus 5 cosine t over 5j. Just gives us negative sine ti plus cosine tj. And they want you to evaluate that at power over 3. for pi over 3, you recall (60 degrees) or pi over 3. This is 1, 2, square root of 3. So the sine of pi over 3 is the square root of 3 over 2. So this is negative square root of 3 over 2i, plus the cosine is 1/2 times j. Okay. So now we find the principal unit normal vector. So we find r prime of t. That's I plus tj. We find its norm. That's the square root of 1 plus t squared. Okay? Everybody with me on that? So now we find, you got to find that tangent vector because the normal vector is based off of the tangent vector. So it's r prime of t all over the norm of r prime of t. So this is 1 over the square root of 1 plus t squared I plus t over the square root of 1 plus t squared j. So now you got to find the derivative on that. Right? So I'm going to rewrite it. Write this first part as parentheses 1 plus t squared to the negative 1/2 power I. We'll leave the second one as is. So we find its derivative. This is where the algebra comes in, right? So we take the derivative of this. This is negative 1/2 times 1 plus t squared to the negative 1/2 minus 1. That's negative 3/2 times the derivative of the inside. That's 2t times I. Plus, now for this jth component, we use the quotient rule. The derivative of the numerator is 1 times our denominator, the square root of 1 plus t squared, minus the numerator, times the derivative of our denominator. So that's 1/2 times 1 plus t squared. 1/2 minus 1 is negative 1/2 times the derivative of this inside. Use that chain rule. This is 2t, and this is all over our denominator squared, j. Now we got to simplify all that. Yeah, I know you don't like it. I don't like it either, but suffer it be so now, for it becometh us to fulfill all righteousness. So that's a good application of that scripture, right? That's what the Lord said to John the Baptist, because John didn't want to baptize him, and the Lord said, suffer it be so now. We got to fulfill this. So anyway, negative 1/2 times 2t is just a negative t, and then downstairs you have that 1 plus t squared to the 3/2 power I, plus this guy up top there is 1 plus t squared, the square root of that, then minus, see 1/2 and the 2 cancel. I have left a t and a t, so that's minus t squared over the square root of 1 plus t squared, and that's all over 1 plus t squared times j. do some more simplifying. LeBron James. So t prime of t is equal to negative t over 1 plus t squared, 3/2 power I, plus this numerator up here. Here's what I'm going to do. I'm just going to use what I know from fractions. I'm going to add these two fractions, combine them, find the least common denominator. This term here is the square root of 1 plus t squared over 1, and this denominator is the square root of 1 plus t squared. So I'm going to have a common denominator of the square root of 1 plus t squared. So I'm going to multiply this denominator to this guy and then to the 1. Right? Then after that, I can combine the numerators, all over 1 plus t squared. You do it a couple of times, and then you kind of get the trick, and then you kind of skip a lot of that stuff and just get to what you want to get to, but I won't do that now. So this is the square root of 1 plus t squared times the square root of 1 plus t squared all over the common denominator of the square root of 1 plus t squared, and that's over 1 plus t squared. That's times j. So t prime of t is equal to negative t over 1 plus t squared to the 3/2 power I, plus multiply those radicals together and you end up with 1 plus t squared minus t squared all over this square root of 1 plus t squared divided by that 1 plus t squared is really this fraction here divided by that 1 plus t squared, which becomes the square root of 1 plus t squared times 1 plus t squared, and that gives you 1 plus t squared to the 1/2 plus 1, that's 3/2 power. The t squares up top cancel out, and so you end up with t prime, not t double prime. T prime of t is equal to negative t all over 1 plus t squared to 3/2 I plus 1 over 1 plus t squared to 3/2 j. Now take the norm of that. So we have the norm of t prime of t is equal to the square root of that negative t squared plus that 1 squared all over. Denominators are the same, so it becomes that same term squared, 1 plus t squared, the 3/2 power, and that's squared. That just becomes this, the square root of t squared plus 1 all over this bottom is in that radical, so this is 1 plus t squared to the 3rd, but it's the square root of that, so that guy becomes 1 plus t squared to the 3/2 power. Your denominator, it stays the same when you pull it out of the radical. So the norm of t prime of t is equal to, now these are two radicals. That denominator is the square root of 1 plus t squared times the square root of 1 plus t squared. So all I have left is 1 over 1 plus t squared. See, this guy right here is the square root of t squared plus 1 all over 1 plus t squared times the square root of 1 plus t squared. So now the normal vector, what they were looking for, this is t prime of t over the norm of t prime of t. And what was t prime. T prime is the negative t over that term there, I plus 1 over that term. And it's divided by this 1 over 1 plus t squared. Right? So this becomes negative t times 1 plus t squared over, this is 1 plus t squared times the square root of 1 plus t squared I plus 1 times 1 plus t squared all over one plus t squared times the square root of 1 plus t squared j. I broke down that denominator to show you what's canceling out. This guy is canceling with that, and this is canceling with that. So we end up with the normal vector is now negative t over the square root of 1 plus t squared I plus 1 over the square root of 1 plus t squared j. And they wanted you to evaluate that at some number t. T is equal to 2. So n of 2 is equal to negative 2 over the square root of 1 plus 4, the square root of 5i plus 1 over the square root of 5j. Yeah. Makes your hand tired. Let me show you the one that on the test, how the test problem will look like. Let's see if I can find it. Oh, you want one like this. That's what you want. Sir? This guy. You want one like this. Let me show you this, and then we'll go. Yes, sir. So r prime of t is negative 6 sine ti plus 6 cosine tj. And then the norm of r prime of t. When it's a circle like that, you see that the norm is just going to be 6, right? Because of the nature of that sine, that cosine. So the tangent vector, we're just dividing r prime by its norm, so that's just negative sine ti plus cosine tj. Take its derivative. See how that's a whole lot better than that previous one, right? So this is negative cosine ti minus sine tj. Its norm is equal to 1. So the normal vector is the derivative of the tangent divided by its norm So the derivative of the tangent is that negative cosine ti minus sine tj, and it's divided by 1. And then you evaluate that one at t equal to 3 power over 4. It's negative cosine 3 power over 4i minus sine of 3 power over 4j. So 3 power over 4 puts you in the second quadrant. So over in the second quadrant, x is negative and y is positive. So we get negative times here a negative 1 over the square root of 2 I minus here that sine of 3 power over 4 is positive. This sign here is already negative. 1 over the square root of 2j. So we have 1 over the square root of 2i minus 1 over the square root of 2j. Okay. So I'll stop here and then I'll finish this section on Thursday, and we're also finished with section 12.5. 12.5 is very easy, very quick, no more than 5-10 minutes on that. There's more left in this section. Obviously, that normal vector, if you have polynomial terms, that becomes very long to try to find. And so if you have something like that, if they asked you, we hadn't even asked to find the normal component of acceleration, to find the tangential component of acceleration, they require capital T and capital N again. So you have to go through all of this. But you put this information together, you put capital N, capital T together, and then you find the acceleration. The acceleration is R double prime, and then take the dot products, and that gives you A sub N and also A sub T. So we'll talk about that on Thursday morning when you come, and then cover 12.5, and I think you'll be ready for the test. Okay, thank you.